let's take this and let's find some equations then for it. Well, the equations that we have for projectile motion are the very same equations that we used for one-dimensional kinematics. Remember, an object moving in a straight line, whether it's in y direction or x direction or otherwise. But because we have a few assumptions, these equations are going to change a little bit. Let's say we have our baseball player once again, okay? And he throws a baseball like that. And the baseball is a projectile, all right? It is launched by the baseball player. It's him throwing it over his head right there. There's a baseball cap rim. And when he launches it, he throws it upwards at some angle. Okay, that angle right there. If you want to throw it any distance, you have to launch it at an angle. Those of you who have played Angry Birds for any amount of time know that you've got to angle your projectile up in order for it to go some distance. So we have some x component of the motion, right? And some y component of it. And by now, see, we'll call this, I'll just call that y and x. And now you guys know how to break a vector apart into components, because we've been doing that for the past couple of weeks. We use sine and cosine functions to do that. But there's an x and y component of its motion at any one time. There's also an x and a y component of its velocity. It has some velocity in the x direction, and it has some velocity in the y direction as you throw it up. But what's different is when we come to acceleration. Since a projectile is under the influence of gravity only, gravity is the only acceleration. It's the only acceleration. Gravity always pulls downwards and accelerates an object. It's the only acceleration. So the only acceleration takes place is in the y direction. There is no, over here, there's no acceleration in the x direction at all. This baseball is not propelling itself horizontally once it leaves the baseball player's hand. It is simply moving with the same velocity in the x direction that it had when it left the player's hand. However, there is a y velocity, and that's this right here. This is our acceleration of gravity. We might say it's negative g, or acceleration in the y direction is negative 9.81 meters per second squared. So there's no x acceleration, but the y acceleration is only because of gravity. So as a result, we can take our equations that we learned 2-3 chapters ago for one-dimensional kinematics and modify them a little bit depending on if we're talking about the x and y direction. Let's look at this first section right here, this position as a function of time. Now the original equation we used probably looked something like this. Delta x equals initial velocity times time plus 1/2 times acceleration times time squared. It look familiar? I believe that was equation 4 that we learned several chapters back. Well, if you recall, delta x is really only the same thing as x final minus x initial. That is the initial, the final position minus the initial position, and then the rest of it was all the same. That's this right here. So that's essentially what we have over in this top equation right here. But what's missing? Oh, by the way, we put the x initial over on this side. In fact, let me rewrite this entirely. This equation, since we break the delta x, sorry for erasing that, we break the delta x into x final minus x initial. This x right here is really the x final, that is at any one point in time. X final equals x initial because we brought it over from the other side. It's not subtracted from x final, but it's added now. Plus initial velocity times time plus acceleration times time. Look familiar? Okay. Well, let's apply it now just to the x direction. Now, here's where, when we talked about this before, we called x was our generic symbol for displacement. Now when we talk about x, we mean displacement specifically in the x direction. Okay, so in this next equation, x would actually be y, but those are just the, that symbol is the placeholder for what we call displacement. Well, let's look at x right here. Let's consider position as a function of time in the x direction. If there is no acceleration in the x direction, that means that all this, that is times acceleration, that becomes 0. And that goes away, which is where we get our first equation right here. Our final x position is our initial x position plus initial velocity in the x direction. That's what that little subscript means right there. Initial velocity in the x direction times time. That's what we have right here. Okay, how will that be different in the y direction? Well, if we write it the same way, our final y position equals our initial y position plus initial velocity in the y direction times time, just like we have above. But we do have an acceleration in the y direction, right? Plus, we might say 1/2 times negative, well, I'll write it just as, I'll write it as vy. Oh, sorry, acceleration of y. 1/2 times acceleration in the y direction times time squared. What is this acceleration in the y direction? We said it up here. It's negative 9.81 meters per second. So wherever we write acceleration in the y direction, that is always going to be the acceleration of gravity. There is no acceleration in the x direction, only in the y direction. That's what gives us these two equations right here. By the way, this is you can think of that as YF as well. These equations are based off that. So that G you could think of as AY, you might say acceleration in the y direction. That's that right there. But in the y direction, our acceleration is always going to be negative 9.81 meters per second. Let's look at our second equation right here. You might recall that our velocity as a function of time was v final, that is our final velocity, is our initial velocity plus acceleration times time. Remember that? That was probably our first equation that we learned several chapters back. Let's take this now and let's apply this to the x direction. So v, the final velocity in the x direction, is initial velocity in the x direction plus a in the x direction times time. And time is in all directions, so that doesn't have a subscript. But in the x direction, there is no acceleration, right? So that becomes 0. All that becomes 0, and that's what this means right here. This means your v, you might say vfx. By the way, whenever you have vi or vo, you know that that means initial or original. Wherever you have just v or whenever there's no subscript, you can assume that that means the final velocity or final acceleration or final position. Just like up here, I had to put that xf in there because there was no subscript, but that simply means the final at that point in time. This means the final at that point in time as well. So that's where we get this equation from. It's the same equation that we used from before, but because in the x direction a goes away, it becomes much simpler. So in the x direction, the initial velocity is the final velocity. Remember, we're ignoring friction, And so whatever velocity you start with in the horizontal direction, it's that same velocity whenever it gets to its destination in the horizontal direction. Okay, let's now apply this to y. Velocity final in the y direction equals initial velocity in the y direction plus acceleration in the y direction times time. Well, we know that acceleration in the y direction is negative 9.81. So this looks a lot like the original equation. We just put in g right here for the acceleration. G is acceleration in the y direction. Again, there is no acceleration in the x direction. And finally, this I believe was our equation 5 that we derived from before. Velocity final squared equals velocity initial squared plus 2 times the acceleration times the displacement, 2ax or delta x. Okay? Well, once again, let's just put some x subscripts here. Let's just say this is in the x direction now. Velocity final in the x direction. Velocity initial in the x direction. The acceleration in the x direction, which there is none, right? So that whole section goes away. And if you look at this equation right here, velocity final squared is velocity initial squared, that makes sense because that's basically that same equation. So if those two are equal to each other, the squares of those two will be equal to each other as well. And how about this last one here? This doesn't change very much, even though we made some substitutions. Velocity final in the y direction squared equals velocity initial in the y direction squared plus 2 times the acceleration in the y direction times a change in the y position, or the y displacement. This is very much the same as that. You might just call it minus 2g delta y, or you could say plus 2 times ay delta y, but make sure you substitute in negative 9.81 in for ay. Our acceleration in the y is always going to be negative 9.81 meters per second squared. So that's where we get these equations. They're very much like what we're used to using, but they're modified a little bit because there's no acceleration in the x direction, and the acceleration in the y direction is always going to be negative 9.81 meters per second.